So we are going to discuss the argument principle. The argument principle. Before I state the theorem, so just recall that if fz is a complex value function, then say for example fz equal to z square, we know that fz equal to 0 for z equal to 0, and how many times that 0 appears, that means what are the roots of fz equal to 0? This implies that z square equal to 0, so that implies z equal to what? 0 and 0. So we say that z equal to 0 is a 0 of z square with multiplicity 2. Okay, so similarly z minus 1 whole square and z minus 3 whole cube, say. So this is your function fz. Then we know that fz has zeros at what? At z equal to 1 and z equal to 3. But if I count the multiplicities of the zeros, then how many zeros of fz are there? There are actually 5 zeros of fz. Okay, and what are those? Those are z equal to 1, 1, then 3, 3, 3. That means multiplicity of the 0 z equal to 3 is 3, and multiplicity of the 0 at z equal to 1 is what? 2. So total, what is the total zeros of fz? There are 5 zeros. Maybe some of them are the same, but with counting multiplicities there are 5 zeros. Similarly, the same case holds for poles. For example, fz equal to say 1 by z minus 2 whole cube, and z minus 4 whole to the power say 5. Then you notice that this function has poles at z equal to 2, and what is the order of that pole? Order is 3. Similarly, this function has a pole of order 4, pole at z equal to 4 with order 5. So what are the number of poles of this function fz? There are actually 3. Order is 3 and another order is what? 5. So the counting multiplicities, the number of poles of fz is equal to 8. Okay, so that is called the poles and zeros with multiplicity. Okay, so that is how we count. All right, so now we state the argument principle. All right, so this is the theorem. So let's see C be a positively oriented simple closed contour. Okay, so this is say positively oriented simple closed contour C. Suppose that number A, that fz is meromorphic, a function fz is meromorphic in a domain interior to C. That means this inside C, fz is meromorphic. And what is a meromorphic function? A meromorphic function which has the only singularities of that function are what? Poles. Only poles can be the singularities. Alright, so that is called a meromorphic function. For example, this is a meromorphic function because the singularities of this fz are just poles, and poles are at z equal to 2 and z equal to 4, and with multiplicity what is the total multiplicity? 8 poles are there. Okay, so our fz is that type of function. Now number B, second condition is that fz is analytic and non-zero on C. So fz is analytic on C and fz is non-zero. That is what? Fz is never equal to 0 for all C. Okay, fz is never equal to 0 for all C. All right. The number C is there. N is the number of zeros of fz counting multiplicities. Okay, That means we are counting the multiplicities. Some of the zeros may be equal, but we are counting all as different. So then P is the number of poles of fz. Okay, counting multiplicities. Okay, so these are the conditions. Then the argument principle says that 1 by twice pi, the change of argument over C of fz, change of argument of fz over C, that means this is, we already know that this is the winding number. Okay, and that is given by n minus p, that means number of zeros minus number of poles. Okay, so this is known as the argument principle. And what is change of argument of fz? So we have the positively oriented simple closed contour C, and if we take the parametric form of C and vary t over C, then the image curve tau will also change, and that will be a closed contour. Okay, closed contour, not necessarily simple, and the change of that argument of fz is given by twice pi times of number of rotations. Okay, number of rotations of this curve. That means how many times it had rotated. So we have already seen this type of curve. Okay, all right. So how many times it is rotated through 0, and because your fz is never equal to 0, so the image curve will never pass through 0, but it will what? This will rotate around the origin. Okay, so this is number of times it actually rotates. Alright, so that is called a winding number, and the argument principle says that the winding number is given by number of poles minus number of poles, counting multiplicities. Okay, so in the next slide we will try to prove this theorem by considering two different situations, and we will arrive at this final result. So this is one of the most useful results in this unit. Okay. So, and we will give some applications of this theorem. Thank you.